back to the Cracking Fan YouTube channel. Today we're going to be solving Leetcode problem 286, walls and gates. Before we do that, just make sure you drop a like and a subscription to the channel. It really helps me grow. You guys know the drill. Alright, you are given an m by n grid rooms initialized with three possible values. A -1, which represents a wall or an obstacle, a 0, which represents a gate, and infinity, which means an empty room. And we'll be using 2 to the 31 minus 1 to represent infinity. For each empty room, we want to fill it with the distance to its nearest gate. If it's impossible to reach a gate, it should be filled with infinity, which actually it already is filled with infinity. All right, so what we want to do is look at an example now, right? So we have the gates here, this little red thingy, and we want to basically fill each of these blank tiles with the distance to its nearest gate. Obviously, these are like walls, they're obstacles. They don't really have a distance to their, nearest gate. So what we do here is, all right, well, what about this tile? What's the nearest gate, right? We can either go one step to this one, or we can go 1, 2, 3, 4 to this one. Obviously, this one is closer, so it's 1. Similar with this one, we have 2 steps to the nearest gate, 1, 2, or we could go 1, 2, 3. Obviously, 2 is smaller than 3, so we go with 2. With this one, we have the option of 1, 2, 3, 4, or 1, 2, 3, so that one's 3. Here we have the option of 1, 2, 3 to this gate, or 1, 2 to this one, so it's 2. This tile is right next to the gate, so it's just 1. Same with this one. This one is going to be 2 to this gate, 3 to that gate, and then 4 to that gate, right? 1, 2, 3, 4. So pretty simple when you're just looking at it, and it's easy to kind of figure it out if you were just looking at this on its own. But how do we actually code this up? Let's think about this. We looked at a simple example, but it's not exactly clear how we want to code this up. Well, if we read the question prompt, we want to, find the distance to the nearest gate. So, we've done a lot of these questions where we have a 2D grid, and we can kind of think of this as a graph where each of the tiles are connected, and since we're looking for the shortest path to something, that immediately tells us to use a breadth first search. So we know that we need to use a breadth first search algorithm here, but it's a little bit tricky because we have multiple gates, right? If we just had one gate, then it'd be easy to just, calculate the distance each one, no problem. But what happens when we introduce, a second or a third or a fourth or a fifth or however many gates we want? Then it becomes a little bit trickier because we need to find the shortest one to the nearest, the shortest path to the nearest, gate. We can't just do to, any arbitrary gate. It has to be the one closest to it on a tile by tile basis. So what we want to do first is actually find all the gates. And that's going to be how we're going to kick off our BFS. So we're going to say find gates and then put into a queue, right? So we're going to find all the gates, put them in a queue, and then what we're going to do is we're going to kick off a BFS from each of the gates, right? And we're going to go in all 4 directions, and we're going to start exploring the grid. And what we're going to do is when we reach a tile, we're going to check the value of that tile. So remember that empty tiles are going to have minus or just regular infinity as their value in the beginning, right? So what we're going to do is, because we do a BFS, we're going to be storing the x coordinate, the y coordinate, and the distance that we've traveled from that original gate as part of our, each item in the actual queue. So once we hit a new tile, we're going to compare the distance with whatever the current grid value is, right? So we're going to say versus grid of whatever our current position is. And if this distance here is actually less than the distance that we have marked already, then we're going to overwrite this and just say that it's now distance, because we've now found a distance to a gate that's closer than what we had before. So we're going to do this until basically we don't have any more things to process. So once we hit a point where, if the distance is actually smaller, then we continue because there might be other things we can overwrite. If the distance that's already there, represented by, grid of, xy, is actually smaller than our current distance, that means that everything past this point is actually going to be a better solution than our distance, because if our distance is already too big, then going even further will make the distance bigger, and we're not going to get better solutions. So we can actually cut our BFS for that branch off, and basically the queue will, contain values that we keep needing to process, and the BFS will continue until basically we found our best path for all of the gates, and then at the end we can just return our final grid because we're going to be overwriting it as we go. So if that's a little bit unclear, don't worry, it's just a standard BFS. Again, the first thing that we're going to do is just parse row by row, column by column to find all of the gates, put them in the queue with the format of the current X position of the gate, the current Y position of the gate, and the distance we've traveled from the gate. Obviously in the beginning this is going to be 0 because we haven't traveled anything. Then we're going to kick off our BFS from all the points simultaneously, and we're going to be basically trying to overwrite the values of each tile with the distance to that nearest gate. And then if we find a better value, so if our distance here is actually less than whatever the value in the grid is, then we overwrite it. If it's not, then we can stop our BFS for that run there, because going further will not actually yield us a better solution, because we already have a solution that's better than ours. Obviously, if we continue, we're just going to, we're going to get further and further away. So if the answer is already too big, then we don't want to continue because it's just going to be even bigger. So that's how we want to do it. Let's go to the code editor and actually type this up. It's a really simple problem. We've seen this kind of pattern before. We're back in the code editor. Let's write this up. So we know that we're going to be using a breadth first search solution. So let us define the queue that's going to be storing our BFS, right? So we're going to say queue equals collections.dec, and we're going to pass in an empty list at this point because we haven't found any gates. Now we're going to be iterating row by row, column by column. So let's define some helper variables to help store the number of rows and columns. So rows is going to be length of rooms, and the number of columns is the length of rooms of 0. And you'll actually want to make sure you define these instead of doing it in line every time, because the test cases for this problem are quite large, and you actually might get TLE if you find this value each time. I found that I had to create these variables to get it to work, even though the solution is the exact like Leetcode preferred one, so it's just weird. Anyway, so now let's actually find all of the gates. So we're going to say for row in range rows. We're going to say for column in range columns. We're going to say if the row column position is a 0 in our grid, then that means it's a gate, so we want to add it to our queue. So we're going to say queue.append whatever the row column value is, and we're going to put a distance, and that distance represents the distance to the gate. Obviously it's 0 in the beginning because we haven't traveled anything. So now we will have found all of the gates if they exist, and let's put a check for that, because it could be the case that there are no gates in our grid here. So at this point we would want to just return just our rooms. So we're going to say if not queue, we just want to return, and remember that we're not actually returning anything, we're just modifying rooms in place. We don't actually have to return rooms here, we just return. Okay, so now we're doing a BFS and we're going in all 4 directions. So let's define those. So we can go 0, we can go this way, we can go that way, go this way, and then that way. So that's all 4 directions we can travel. Now let's actually perform the BFS, and I'll just close this here to give me more space. And we're going to say while queue. So while we have something left to process, we're going to say the current row, the current column, and the distance we've traveled equals queue.popleft. And now what we want to do is we want to check whether or not our distance is actually a better solution than whatever the distance that's in the current rooms for that current row and current column. And we're going to do that by saying if distance is actually less than or equal to rooms of current row, current column, then we want to basically overwrite that distance. So we're going to say rooms of current row, current column, is going to be equal to this new distance. And now what we want to do is actually continue our BFS in all 4 directions. So we're going to say for row increment, column increment in directions. What we want to do is we want to get the new row, which is the old row, so the current row, plus whatever the row increment is. And the new column is going to be the current column plus the column increment. Now what we want to do is make sure that this new row and column index within our grid is actually valid. So we don't want to have an index error by, checking an index that doesn't exist in our grid. And we also don't want to go to an obstacle. And remember that obstacles are marked with -1. So there's no purpose of us going there because there's nothing we can do with an obstacle. So let's do those checks. So we're going to say if, let's check that the new row is within the bounds. So new row is within the bounds of our grid. And we want to check that the column is within the bounds of our grid. So new call less than calls. And we want to make sure that rooms of new row, new call doesn't actually equal to an obstacle. If all these things are true, then we can say q.append our new row, our new column, and the distance +1, because now we'll be moving 1 tile. So this logic will continue while we have something to process, and when we're done, we can simply return. So I'm just gonna run this, make sure I didn't make any syntax errors. Int len rows, rooms. Okay, cool. Yeah, that's why I do that. All right, cool. Doesn't seem like I made any other mistakes. So let's submit this and zoom out a bit. Test cases are quite large. Yeah, don't TLE me. It literally just accept. Oh my god, are you kidding me? Okay, let's just see if this does it again. Leetcode. It literally ran 6 minutes ago with the exact same code. Oh, I hate Leetcode, man. Leetcode seems to be extremely difficult today. Even though I submitted the exact same code about 6 minutes ago, it is now TLEing, which is ridiculous because if we look at the actual example or the solution, then they literally do the exact same thing we did. Searching from empty grids. Okay, so initiate a breadth first search from all gates at the same time, which is literally what we've done. Their code is exactly the same as what I've written, but for some reason, okay, now it accepts, this is ridiculous. I have no idea why Leetcode does this. It accepted, then time limit exceeded, then accept. Okay. Anyway, I'm gonna stop complaining because I'm just gonna pull my hair out here. So the time complexity for this algorithm, obviously we have to parse the entire grid here to find all of the rows and the columns. So doing that is gonna take big O of m times n, because that's the dimensions of the grid. Then we have to basically traverse the entire grid again in our BFS. So that's also going to be a big O of m times n. So we see that this is really just big O of m times n, 2 times big O of m times n, which asymptotically is just big O of mn, right? Space complexity, we have our queue here, which is holding, our elements that we have in our queue to represent the breadth first search, and the amount of elements is going to depend on the size of our grid and how many gates we have. So this is going to be big O of m times n. So that is your time and space complexity. This is the most optimal algorithm, despite Leetcode for some reason accepting it sometimes, not accepting it other times. Literally, nothing changed between these invocations. I don't know why this one was almost twice as slow when literally the code is the exact same. I guess the machine you get to evaluate it, I don't know, some of them are faster than others. Distributed systems for you. All right, anyway, I'm gonna stop rambling. As you can see, the code works. This is the most optimal solution. Obviously, if we look at the solution here, it's a breadth first search, starting from all the gates, which is what we did. And as you can see, there's no solution better than ours. So for some reason, it's not being accepted. But yeah, you'll just have to trust me that this is the best one. And as you can see, even from the solution, that is the best solution. So I'm going to stop rambling because this question has pissed me off enough already. And there you go. So that's how you solve walls and gates. This is another one of those BFS questions in a grid. If you like this video, please leave a like and a comment. Subscribe to the channel because I'm pulling my hair out trying to make these videos dealing with the nonsense that is Leetcode. Yeah, thanks so much for watching and have a great rest of your day.